Hi everybody, Adam with FANUC here. Gonna talk today about some setting up of user frames, why we do it, and some useful tips and tricks. Um, if you're an advanced user and you know how to set up a user frame, but you want to get to some more advanced stuff, just skip ahead in this video a little bit because this one's gonna be a two-for-one. We're gonna lay some foundational knowledge at the beginning on what they are, why we use them, how we set them up. Then at the end, I'm going to show a neat little trick. So let's dive in here. As we go through this, I just want you guys to think about your applications and where a user frame fits in. Okay, so at its core, a user frame is going to define an origin and a plane where all the positions that you teach are relative to that position. So right now on my screen, you can see my robot's tool frame. All right, I've defined the tip of this pointer tool as a tool frame. And you can see on the screen, let me make some movements here. You can see on my screen the Cartesian coordinates of where this is. You can see that in X, I'm 1,154, and Y, I'm 338, and Z, I'm 667. You can see that here too on the Teach Pendant screen. But what does that even mean, right? Why do we care? If you look at the top down and you look at where FANUC measures from, we're measuring from the axis of rotation of J1 as it intersects with the plane of J2. So it's the belly button of the robot. It's the one part that will not move no matter where you go in space. You know, everything comes about that. Well, when you're doing work and you're setting things up, just knowing where that pointer is, or your gripper, or whatever, knowing where that is relative to the belly button of the robot is not always advantageous. So I'm going to show you how to set up a user frame to make these coordinates make a lot more sense, and show you how they can really bail you out in a pinch. So let's start off real easy. Menu, setup, frames. When you get here, you might see some other things. It might default to being the tool frame, which I've already set up. But let's press the other key. And let's go down to our user frames. Okay, I've got nothing in the first two right now. I've got them totally blanked out. So let's go in here and hit detail. Start off nice and easy by naming it something. I'm just going to name it table. And we need to teach 3 points. I want you to notice that there's different ways of setting up a user frame. There's a 3-point, a 4-point, and a direct entry. Most of the time you're going to be using 3-point. 4-point is for vision processes. If you've got overhead vision guidance, we need a what they call a system origin so that we have an axis of part rotation. And then direct entries if you just want to type in the user frame data, which you don't always know. So we'll just let the robot figure it out by using a 3-point. So here's what we're going to do. We're going to set up a 0, 0. We're going to set up an orient origin. Think in your head of the right-hand rule, which is actually perfectly portrayed here with if your index finger is X, and you point your middle finger out in Y, your thumb will naturally point up in Z, and that's your triad in space. We're going to build one of those here. So what you're going to do is you're going to jog your robot down to the corner of your workspace. Okay, something repeatable, something that robot can reach. And I'm going to teach that as a 0, 0. I'm going to press Shift, Record. As soon as I do that, you see that my orient origin went from being uninitialized to being recorded. Excellent. Now think about your right-hand rule. This will be our new X plane. So I'm going to jog the robot. You guys will be using the jog keys. I'm cheating because I have RoboGuide. But I'm going to bring my robot up to this corner. Looking good. And I'm going to say that is my X direction. Shift, record. Very good. No surprises here. We're going to come down to this corner, bring the robot down, Y direction, shift, record. The moment that all three are recorded, you see they automatically switched and they say, all right, they're used. You get a little love note that says a new position has been calculated. And moreover, you get some data. Where in the world is this table? And we can look at this data and see that from the belly button of the robot relative to there, the corner of this table is 1199 millimeters out, a little bit negative Y. You can see that it's in the negative direction Y, and it's Z 284 above the belly button, and there's 0 yaw, pitch, and roll because it is perfectly square with the robot. If I show you here, it's square with that robot base. It's aligned. So and it's level. So now we have that. What does that mean? What does that look like? Okay, I want to give you a visual representation that I can give you in RoboGuide that you really don't get in real life. But if I open this guy up and I just click on User Frame 1, look what it does. It highlights where that is. There's that 1199, the 284, the negative 360. But look at it puts my triad XYZ perfectly at the corner of that table. Okay? And this is going to become very, very beneficial for me, all right? And you're going to learn more why in just a second. But there it is. And if you really want to visualize it, RoboGuide allows you to view it as a plane in space. You know, we imagine an infinite plane, but a plane in space. There it is, okay, right on the table. All right, let's get in here and we're going to teach a program. And we're going to start testing why we use these and why it becomes beneficial. So let's make a program together here. Let's just call this guy path or something like that. Okay. All right. So again, I'm going to use my super quick and easy RoboGuide features to move this robot around. You know, it's a little bit easier than jogging a real guy. But let's just start somewhere around here. Let's start making some points. All right, robot, go there. Then I'll say, let's go over here. And then let's go up here. Do a little bit of back and forth zigzagging. You can actually see, you know, RoboGuide is really good about visual representations of things. So it's showing me what this path is going to be and what it's going to become. Let's keep going here. Okay, so we're just making this nice little zigzaggy program, all right? Back and forth, back and forth. I'll go ahead and right off the, well, we'll keep it slow. That way we can actually see it when it runs. One thing I am going to do is I'm going to make it come back to the start position. So here's the path it makes. Zigzag, zigzag, zig, and then back home. So let's go ahead, let's see what we have here. Okay, so let's go ahead and run this real quick just so we can see the robot running in this program. Here we go, run. There's our nice little zigzag pattern, back, forth, back, forth. You see it working very nice, staying right on the table, coming back home. Wonderful. Looks great. A little slow for my liking, so we'll fix that. But that was our path. Now, while I was doing this, while I was setting this up, it's important to note that if I press Shift Coordinate, I can see what tool and what user frames are active while I'm working. And what's important about that is, if I were to open up any one of these points, let's open up position 1. Let's open that. Right across the top, it gives you some information that most people just ignore. But position 1, taught in user frame 1, taught in user tool 1, and then don't worry about the configuration for this, but it's normal and up, and it's telling you the configuration of the wrist to know that it's not at that point in space, but underneath the table. But here's where it starts getting really nice right off the bat. Look at our X and Y and Z data. X, Y, Z. Where is this robot? It's at 87, 100, 0. That's because we are 87 millimeters from the corner. We're 100 over, and we're right at the table, so we're at 0. So the first lesson I want to drive home is it makes the math incredibly easy. Let's look at our position in world coordinates right now. If I were to click off of this, click on that, and go to world. So where we are right now in world, where that tool is, look at from the belly button, we're 1,286 in X, we're negative 259 in Y, 284 in Z. That doesn't mean anything to us, right? We don't know. But if we look at our user, I'm clicking my F3 for user, look at, we're 87, 100, 0. You can see this, 87, 100, and then of course 0. If I were to take my robot and move it up, give it a little Z element there, 87, 100, 41. The math becomes really, really easy just for a user, okay? But let's say, okay, Adam, yeah, math is great, math is easy, I don't care. Why am I doing all this extra work, teaching all these points and setting up my frames just to make my math easy? Well, I'm glad you asked. Let's take this table and let's totally mess it up. Let's move it around, okay? I'm going to rotate this thing on an angle. I'm going to tilt it, kind of make it messy this way. Look at that, it's messy. We're going to move it over. Okay, so now that table is totally jacked, right? Totally cattywampus. If I told you rerun your program, what do you think is going to happen? I'll show you what's going to happen. You're going to crash and you're going to fail. Look at, your robot's going to destroy your table, destroy your parts. It's going to be a mess. Well, what if we go into our setup, our frames, and we reteach our user frame? Let's clear the content of the frame, but not the comment. Let's go into our detail, and let's just take a quick moment, go down to our origin, click record, go to our X, click record, and go to our Y, click record. Now we have a new user frame, and look at some of the differences we have. There's now a yaw and a pitch value. It's because RoboGuide and the robot already know where that table is in space because we just touched off on those 3 points. And now look at what it did. You see my old path in blue. Look at this future path in green. It put it right back onto the table. So now even though the table is completely a mess, just a complete mess, our program completely untouched. Let's run it again. Keep in mind we have not touched up any points or anything. Look at that. There's our program. Let's run it again. That robot now has our program perfectly on that table, even though the table is totally different. So start thinking about your process. What if you have trays or some fixtures or a conveyor? Somebody bumps the conveyor. Somebody takes off a tray and puts a new one in because it's different parts. Somebody relocates a machine or a robot. You might have a program that's got a heck of a lot more than 6 zigzaggy points in it, okay? By using user frames, you can teach it one time and have the robot completely adjust the entire program without ever touching up any points, without touching up the program. Just let it know where this triad is. So that's our second lesson, is not only does math become easy, but taking care of dynamic changes becomes easy. It's lesson 2 of 4 that I want to give you. Here's lesson 3. If I wanted to jog around this table, right? Right now I'm cheating because I have RoboGuide. I can just point, right? That's money. But what if I actually want to use my teach pendant like someone would? Look first. I'm going to slow this down so you can watch. Look first right here. I am in world coordinates. Watch what happens if I take this robot and I tell it to go -x in world. Think about where it's going to go. Think of the world coordinates of the robot. Think about what x, positive and negative, are going to look like. Where's it going to go? I got to turn it on to show you. Here we go. It's going straight back. All right, I can bring it back forward again. Straight forward. That's our x direction of the robot. But what if I toggle this? What if I go to my coordinates key and I toggle it so that it highlights user? Now watch what happens when I hit X. It follows the table perfectly. It follows the angle that that table is on. So if I wanted to run a Y direction, there's Y. Let's go with Y negative. That robot is following the table perfectly as I jog with my teach pendant, even though, look at this thing. It's angled, it's tilted, it's yaw, pitch, roll, crooked. You would never be able to follow this table without user frames. Couldn't do it. Because in a world system, if I did plus Y, there it goes. I'm going right through the table. I'm crashing. I'm destroying company dollars. It's getting worse. Wrecking a robot, right? Look at it. Makes a mess. So in world coordinates, or if you have no user frame set up, to follow this path, you'd have to have all combinations of XY, 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 even some combinations of Z, -x, -z, -x, -z. It's a hot mess. So lesson 3, why do you use user frames? It's just to help you teach the points. You can jog so much easier. I can even use my Z and show you what a normal vector looks like to the table. Helps if I'm in, see right there, that was world. Let's go into user. User plus Z, straight away from the table, straight into the table. No guesswork. So that's the 3rd lesson. Okay. Now, let's get into the 4th lesson, which is a little bit more advanced. Please master this first step first. Make sure you know how to set up your user frames. Make sure you understand what they mean, how they work. Make sure that means something to you before you get to this next part. Because what I want to do is I want to take this table and duplicate it. And I'm going to take another table. We'll just put it, make sure it's within the reach of the robot, but we'll just put it somewhere crazy and over here. All right, I'm sure the robot can reach this. Let's do a little test. Yep, perfect. Okay. So now I've got another table over here. Let's do one quick review. Remember that when I teach a P, a position, it remembers user frame and user tool. That's going to be important for this next bit of information. I'm going to delete this code. Don't need it anymore. And I'm going to open up my position registers. These are not P's. They're not local positions. These are position registers, PRs. These are global. So let's go back here. We're in user 1 and tool 1. Let's go back to this original table, this original program. I'm going to go right here and I'm going to reteach everything but with PRs. There's PR1. Go over here. Here's PR number 2. Go here. PR3. Here. PR4. And I'm rebuilding this program line for line, going to make it exactly the same as it used to be. Okay, but with PRs, let's go back into that path program and let's rebuild it. Linear, I want to go to PR number 1, 300. And then let's do some copy paste, copy, and paste 2, 3, 4, 5, 6, and back. All right. So here is our program. Let's run that real quick, make sure that it does exactly what we expect it to do. Perfect. So there's our nice little zigzaggy program. So you might be saying, Adam, why did we delete 6 positions and then rebuild 6 positions? I want to show you something. When you open up the position data of a PR, look at how it's recorded. No longer does it say user frame 1 and user tool 1. It says F. This is because whatever frame, F, whatever frame is active is where these coordinates matter. I'll say that again. Whatever user frame we have active, which right now, shift coordinates, our active frame is user 1, this robot is going to go to 89.6 by 105 by 0 of user frame 1. Well, we know that user frame 1, if we go 89, 105, 0, we get here. But what if we built a different user frame? What would happen? Menu, setup, frames, frame 2. Let's name this guy table 2. Orient origin. Go down to my corner. Click, record. Go up here. Click, and record. Go down here. Click, and record. So now we have information about where that table is. We'll double check here by clicking on it. Yep, there's my triads. So remember how I told you in the program, when using PRs, it only cares which one is active. Let's do shift coordinates, and let's make user 2 be active, right? It used to say, I'm just going to show you, it used to say user 1. I'm going to make it say user 2. Perfect, like that. And let's run this program. We are now running that exact program that we built on the other table. We're building that exact program on this table. So now, by only teaching 3 points, a 0, a X, and a Y, by teaching 3 points, we've translated an entire program. Now, you've seen me before in my videos put in my favorite lines of code, right? And I'm going to stress it again. My favorite lines of code are: what frame are you working in? What tool are you using? How heavy is your equipment? And how fast would you like to run? We'll leave that at 100. So if you tell the robot frame 1, tool 1, right in your code, that robot's going to go over there and run the program. Now, let's take it a little bit further. I can take this exact piece of code, let's highlight the whole thing, select, take this whole code, copy, come down to the bottom and do a paste. Okay, so now I have the same code twice. Let's put some separation there and say user frame 2 for the second round. So look at this code, starts with U frame 1 and does the zigzag. Then it switches to U-frame 2 and does the zigzag, all in the same program. I'm not even making a new program. It's all within the same program. Let's run this. There goes the robot on U-frame 1 doing a zigzag, and then it immediately goes over and makes its zigzag on U-frame 2. So now you should already mentally be thinking about the benefits you could do here. What if you have multiple stations? You're tending multiple machines, multiple conveyors, multiple trays, multiple pallets. Robots do a lot more than just one thing at a time. If you're going to repeat a pick and place code or a paint code or dispense code or anything like that, you can truthfully benefit by writing the program once and then just telling the robot what frame to do it in. It's the same code, it's the same path, it's the same logic. I just want you to do it over here instead of doing it over here. And that's the fourth and final lesson, is you can write modular code, real clean, real nice code. In fact, if you really want to get fancy, an experienced programmer would look at this and do something like this. Let's say, Adam, we don't need to copy and paste that code. Let's delete everything on that second half. Let's go back up here. Let's encompass this with a for loop. You can really make some nice code. Say for register 1, running from 1 to 2. Add in the line that I just accidentally deleted. And what frame do I want to run? I want to run the frame that has the data that's in R1. So for when R1 equals 1, we'll be running U-frame 1. And when R1 equals 2, we'll be running U-frame 2. So then we just go to the bottom here and just end that for loop, for, and for. So now we truthfully only wrote the code one time. We didn't even copy and paste it. Let's run this bad boy. Here it goes. Let's start over at table number 1, doing our zigzags. Come back over, run table 2, do our zigzags. You can really clean up your code, really save yourself tons and tons and tons of time, and you can really do your future self a favor when things change in your work cell and you need a quick fix. You teach 3 points and everything goes back the way it should. You might get into some fun, heated debates with people who say, hey, you know, our maintenance guys don't know how user frame works, so it's easier just to teach everything in world. Okay, well, then you're going to be teaching 12 points instead of 6, and you know, if a problem happens, you're going to be reteaching 12 instead of just 3 user frame points. But if that's the price you got to pay, that's the price you got to pay. I love having the debate with people because in some cases, a user frame could be more work than it's worth. Let's say that this table, let's say this was a little robot and it was mounted on the table. Well, now when the table moves, the robot's moving with it. So you don't need to teach a user frame if what you're working on is physically attached to the robot. But if there's any opportunity for any changes or slop or repeated work or issues with jogging along a crooked plane, maybe your table's just not perfectly level and you're sick of going X and then 2 millimeters down in Z, just teach a frame and be done with it. Your future self will thank you. If you have questions or if you have any questions, comments, put them down below. You can always contact us at 888 FANUC US. And guys, get out there and have fun coding.